Hello everybody. So we have the pleasure today of welcoming László Székelyhidi from Leipzig, who will talk about magneto-hydrodynamic turbulence, weak solutions, and conserved quantities. László, the floor is yours.
Okay, thank you very much for the introduction, Anne-Laure, and thank you for the invitation to the Laboratoire Jacques-Louis. Since there are so many Zoom talks with slides that everybody is watching for the last year, I thought I'd try something else. It's basically like a Blackboard talk on paper. But if you have trouble reading or seeing anything, please try to let me know. I will try to see also the look at the chat. Okay, so this is the subject. Also, this is somehow a mixture between some technical stuff, but I'm trying to also give an introduction to MHD, at least how I understand it and what are sort of interesting mathematical issues that have been addressed recently. And in particular, I will talk about weak solutions and conserved quantities. And this is all joint work with Dani Farako from Madrid and Sauli Lindberg from Aalto University in Finland. Okay, so to begin with, let me just give a basic introduction to the model. So I will focus only on the incompressible case. And so basically, the MHD system is a coupling between Navier-Stokes or Euler and Maxwell or the Faraday system. So this is the first equation, the momentum equation. And then the second one is for the magnetic field B. Equals eta Laplacian of B, and then we have that both of these vector fields are supposed to be divergence free. So I will be concerned entirely in domains in R3, either the periodic case or R3 itself, but no boundary, just for simplicity and because there are certain effects in non-simply connected domains or domains with boundary that I don't want to mention. So just to walk you through briefly this model. So first of all, this B dot grad B term already has its origin in the so this is the Lorentz force. It is usually in physics books written as the magnetic current. So the current cross product with B. This is the Lorentz force. This term, this curl of B cross E. Sorry, I made a mistake. It's not E, it's U. It's the velocity U, and so B cross U is part of E, and this eta Laplacian of B is also part of E. So this system is then dTB plus curl of E is equal to 0, and that's just the Faraday system, part of the Maxwell system. And so the coupling to this J and E is two more laws from magnetodynamics. One is Ampere, which is that the current is given by the curl of B, and the second one is Ohm, which is that E is equal to 1 over sigma, the resistivity, times J minus U cross B. And this 1 over sigma is eta, which is called the diffusivity, magnetic diffusivity, or resistivity. Okay. So one speaks of the viscous, resistive, MHD, incompressible system. That means if these two parameters are positive, and the ideal MHD is when they are 0. Okay, so that's the basic modeling aspects. Now, next I want to talk about some conserved quantities. It turns out to be a very rich system, somewhat more interesting than let's say Euler, Navier-Stokes. Although at this point I can already tell you that that you can probably see that if B is equal to 0 identically, then the system just reduces to the incompressible Navier-Stokes equations. And if nu is 0, then it's the incompressible Euler equations. So that already gives some idea of the type of conserved quantities one can look for. Okay, so now concerning conserved quantities, there are 3 known quantities, and I believe there's even a proof that these are the only ones. One is the total energy, which is 1/2 integral u squared plus b squared dx. So this would be the kinetic energy plus the magnetic energy. Then you have the what is known as cross helicity, which is u dot b. So this is called cross helicity. And the third one is h, which is the magnetic helicity. Magnetic helicity, and so I will refer to this as helicity. And here A is the magnetic potential. So A is defined by the equation curl of A is equal to B, and divergence of A is equal to 0. Okay, so that's the magnetic potential. And so basically in the case, I mean, let's say focusing on the periodic case T3, this is uniquely defined, and in particular also the magnetic helicity is independent of the choice. So even if we wouldn't have divergence-free condition, this would be uniquely defined, because if you add the gradient, it doesn't change. Okay, so let's say energy balance for these 3 quantities is as follows. This is very simple calculations. The total energy changes in time according to, let's say, viscosity, as in Navier-Stokes, and the same way from the diffusion, the magnetic diffusion. The cross helicity is of the form nu plus eta times the current scalar product with omega, where I just write here again, J is equal to the curl of B, and omega is equal to the curl of U. So it's the current times the vorticity. And of course, you can write this by just integration by parts in the form B dot Laplacian of U or U dot Laplacian of B. And the change in time of the magnetic helicity is given by eta minus eta times J scalar product with B. Okay, so yeah, so basically, I mean, I guess it's pretty apparent from these formulas already that the total energy and the cross helicity play a sort of similar role. And if you treat U and B as kind of equal partners, and they play the same role as the kinetic energy in the case of the Navier-Stokes equations or Euler equations, but the magnetic helicity is a different type of animal. So let me say a few words about what is H. Since this is a more general talk, I hope I'm not boring at least some people. So I will just say a few words about H. And so the key point is H has some topological information. And the easiest way to see this is that H is diffeomorphism invariant. So so the way to see this is that if you take potential one form alpha for the magnetic potential A, in the sense that alpha is equal to, let's say, A1 dx1, A2 dx2, A3 dx3, then d alpha is basically is B. So it corresponds to is a 2 form with entries which are given by B, the entries of B, and A scalar product B times dx is nothing else but alpha wedge d alpha. And so you can see here that applying a diffeomorphism doesn't change the form, doesn't change the integral, the total integral. Okay, so being diffeomorphism invariant means that this term has some topological information, and this is a beautiful theory for which I refer you to the book of Arnold and Kessin, and just mention a couple of examples. So, for instance, if you take a tube with some, so that the magnetic field is basically supported inside this tube with total flux, say phi. Well, whatever the flux is, the H will be 0. But if you take two tubes which are linked, now I will try to just draw the curves with the centers of these tubes, but you can imagine somehow two tubes. Then say with fluxes phi1 and phi2, then H is given by 2 phi1 times phi2. And moreover, more generally, if let's see if I can draw this. So if you have more links between two tubes, something like this. Okay, so this is flux 1 and flux 2, then H is equal to 2 times the linking number of the two curves times phi1 times phi2. Okay, so just to give an example that this is the type of topological information, and of course for a general field there is a version of this counting links. What I think Arnold introduced that, the asymptotic linking number, but I don't want to go into this. Let me also just mention that, of course, this is analogous to the Kelvin theorem in Euler. Okay, so the B equation can be written in the form dTB plus U dot grad B minus B dot grad U equals 0. And you see, if you replace B by omega, the vorticity of a solution of the Euler equations, this would be the vorticity equation in 3D. And out of this equation, you get Kelvin's theorem, which is a conservation of vorticity along curves that are vortex lines, vortex curves that are traveling with the flow. Okay, so now what I want to mention next is what is called the relaxation theory. In the turbulent in the MHD literature, and for that one, so the first observation is that if you look at the decay rates, well, decay is not so clear because they're not definite quantities except for the energy. if you remember, so these are the rate of changes for these three quantities, and you see that the total energy and the cross helicity involve integrals which have one derivative on each of u and or b. So it's L2 based with one derivative, or you can put, of course, one derivative on two derivatives on one of them. However, the helicity is again an L2 type quantity, a product of two things, but basically just one derivative, right? So so it's B and J has one derivative of B. Okay, so it's a lower order if you just count number of derivatives and number of terms, and the consequence of this is that basically in terms of scaling, the rate of change of total energy and helicity is much bigger than the rate of change of helicity. Of course, it's a very rough way of saying it, but this leads to the observation, which is physically observed, that there are two timescales for how these energies change in time as t goes to infinity, or evolving in time. And so, roughly speaking, and this is the basis of the Volcker-Taylor relaxation theory. From 1950 was the paper of Volcker, 1970s was the paper of Taylor. So basically, the type of picture one observes is that, let's say, the kinetic energy, which is part of the total energy, would decay at a certain rate. Let's say this is just a cartoon picture of k, but at the same time, the helicity would decay at a slower rate, and of course, it will not really go to zero. Now, the theory developed or put forward by Volcker and Taylor to look at the asymptotic state in this evolution is that in the asymptotic state, basically, there's no more kinetic energy, it's essentially zero, but there is some magnetic energy, and asymptotically, what should happen is that the total magnetic energy should be minimized, subject to the constraint that the helicity is given. It doesn't go to zero. It's something, it cannot really change because the rate of change of this helicity is very small. But so, okay, in this process, you should reach the minimum state. That's this Volcker-Taylor theory. And okay, so of course, with the method of Lagrange multipliers, it's very easy to calculate that if you have that, then you will end up with Beltrami fields. Those are the minimum in at least in T3. Okay. Now, there are a couple of difficulties with this theory. So basically, the problem is, well, first of all, that once, let's say, the kinetic energy is essentially zero, then in the electric field equation, we had E is equal to B cross U plus eta times J. U is more or less zero. So this is essentially neglected. And you see, if the electric field would be zero, then there's no way that B can change, because the other equation was Faraday, dTB plus curl of E is equal to zero. So the only thing left is this small number eta times J that could cause for this relaxation. However, so this is certainly possible. There are sort of very nice geometric models for how you can change the sort of let's say reduce the magnetic energy without changing the total topology And one nice example is when you have this linkage, which I drew earlier. Then in this part, there is what is called reconnection. And so instead you get some picture like this. Okay, yes, I think this, okay. So this type of, let's say these two lines are quite close together, then they kind of turn around. Okay, so this will, because one can calculate that if you have a cube with a twist, it also has the same helicity as the link of two tubes. So this will not change helicity, but this sort of cutting and pasting does lead to a loss of magnetic energy. So this was put forward by Sweet and Parker in the 1950s. But the problem is that, okay, so in typical situations, physical situations, you have a value for this eta, which will tell you how fast this type of reconnection can happen. This is called reconnection. And one application for why one is interested in this is to understand the solar corona, in particular solar flares. And according to this type of model, a solar flare would take of the order of a couple of months. So when you have some sort of energy escaping, loss of magnetic energy turning into heat, and at the same time a sort of reconnection. So it would take 2 months. In the experiments or observation, sorry, not experiments, the observations, it's more like 15 minutes. So this type of reconnection cannot explain solar flares. That's somehow the problem. It's way too slow. And by the way, it's already pretty good, this Sweet and Parker, because before this type of model, if you just look at standard diffusion, which could also, also leads to loss of helicity, then a solar flare would take of the order of like 1 million years, which is clearly just not nonsense. Okay, so because of this difficulty that this is too slow. Let me just put this is too slow for certain situations. The more prevalent theory is to do some kind of turbulence modeling, which in practice, well, the first step, it just means a kind of Reynolds or 1-point averaging. And so what this means is that essentially you have a kind of hypothetical decomposition of the velocity into a mean fluctuation, the same decomposition for the magnetic field, and then you apply bar to the equations, and you get, as in the case of Navier-Stokes, something like this. That is, say, u dot bar u, the grad p equal to b dot grad b plus, or let's say minus, divergence of a Reynolds stress term, where this is now, this R bar is of the form, well, let's say it's the hydrodynamic part. It's the difference, well, between first product and then average, or first average and then product, and then you have the same for B. And in the magnetic equation, you just do the same thing. Equals sort of magnetic. So this is, I've written it as a vector field, but sometimes it's written as a antisymmetric tensor. Okay. But this is what you see in books. And then, of course, to get some extra equation for this R bar H and R bar M, there's a closure model. Okay. Now, so this is the let's say the physical state of the art. Of course, then there's more complicated averaging, and there are scaling theories analogous to what happens in Navier-Stokes and Euler. So now let me directly go to weak solutions. So here I just write down this. So this is, I can go a bit quicker. This is already prepared. So of course you can write the equations in divergence form. And if you do that, you can, it means that you can define, I mean, you can talk about solutions as soon as U and B are locally square integrable in space-time, because then the distributional solution makes sense. And motivated by the fact that there is a total energy, the energy space would be defined as L infinity L2. And now I've already taken the ideal case. I should write here. So this is the weak solutions for ideal MHD. Of course, there's an analogous theory for the viscous resistive, but that would be more along the lines of Leray weak solutions. So for the ideal case, this would be a definition of weak solution. And then analogous to what happens in the case of weak solutions of the Euler equations, one can ask what I call the Onsager type question. If I take a weak solution in some space, does it conserve my quantities, the conserved quantities, energy, quantities. So the total energy, cross helicity, or magnetic helicity. And there is a very analogous theory to what happens with Euler. Let me just do it in the hand-waving way. So if you write down the, let's say, the proof of energy conservation in the smooth case, first you write down, I mean, first you multiply the equation by U or B. That would give you these two, or this would be the third equation for getting the helicity. And there's a divergence term. And in order to get conservation of the three conserved quantities, you integrate in space. Now, this only works, this technique, if what you have here is integrable. And the argument that was, I mean, which is basically the argument of Constantin Eulen-Titi for the Euler case, boils down to the following rule of thumb. You have to look at the number of terms and then the derivative, to count the number of derivatives and the number of terms, and then distribute them evenly. And so in particular, if you see here, you have one derivative and three terms. So if, and this is the theorem of Kaflish, Clapper, and Steele, if U and B are in this Biesov space with alpha derivatives in L3 infinity, and alpha is bigger than 1/3, then the energy, oops, this is W, are conserved. So energy and cross helicity are conserved. For the helicity conservation, magnetic helicity conservation, this is one way to write it. And now you see here we have one derivative, you have again three terms, but here you have an antiderivative. So the number of derivatives in total is 0. And so the theorem will be that helicity is conserved if alpha is bigger than 0. And this was then extended by Kang and Lee to the case where U and B are just L3. No derivative. It's like alpha equals 0. Okay, so I went a bit fast, but of course the proofs use the mollifier and commutator type arguments that Constantin Titi used in his paper. Okay, so now I have another prepared page. What about the existence of weak solutions? So as I mentioned, for the viscous resistive case, you can use the Leray-Hopf type solutions. But for the inviscid case, that doesn't work for the same reason it doesn't work for Euler. And in particular, if B is equal to 0 identically, we are back to the incompressible Euler equations. where, of course, there has been quite a lot of work to construct weak solutions which do not preserve the total energy. Now, that type of construction has been extended by Bronzi, Lopez Filho, and Nussenzweig Lopez to what I call 2.5-dimensional flows. So here, if U is just essentially a solution of 2D Euler, and B is in x3 direction, but also depends on your x1 and x2, then this reduces basically the system to 2D Euler plus passive scalar. So it's an extension, I mean, the extension of the techniques leading to weak solutions of 2D Euler can be applied. And there are two recent theorems that are, I mean, more going in the direction that I want to go now. One is by Beakey, Bookmaster, and Vicol from 2020, where they constructed weak solutions in this space continuous in time with H beta, so H is L2 with beta derivatives, but beta is something very small. So for all practical purposes, they are in the energy space, but not really substantially better than the energy space, and they do not preserve anything. So not the total energy, the cross helicity and the magnetic helicity are not constant in time. And with Faraco, Lindberg, what we proved is that the existence of weak solutions which are bounded, and they do not preserve the total energy and the cross helicity. Of course, being bounded means that they have to preserve, this was this result of Kang and Lee, they have to preserve the magnetic helicity. Okay, so they are above this L3 threshold. Okay, so a fortiori they preserve the magnetic helicity. Okay, now let's see, I'm doing with time. Okay, so let me give just a brief idea of how these constructions work. Of course, they are all done by convex integration. But what I want to focus on now is not the technical aspects of convex integration, but the main, let's say, philosophical aspects of it. So roughly speaking, in a nutshell, convex integration is an iterative technique, and at each step, you have some kind of approximation, UQ and BQ. So say you start, and you try to construct inductively this sequence so that they converge to a true solution. Yeah, strongly. Okay, so more precisely, so let me just focus on the case of Euler for the moment. So if B is identically equal to 0, then we are just dealing with the incompressible Euler equations. And at step Q, what we have is an approximation, which we write in this way. So it's not a solution of Euler because there is a certain defect, which is Reynolds stress type. Okay, so this is the, and of course, divergence of UQ is 0. And okay, so this is the error term. If this, we want to get this to be 0 eventually in this sequence, and so the idea is, I mean, the main point is how to choose the next. I mean, UQ plus 1 should be UQ plus some W, where this W, that's somehow the key point in convex integration, I would say. Well, the first point. This is what you have to solve first. Which is a highly oscillatory ansatz. So it's a periodic function, which somehow then has to be fit to UQ. And the key properties of this W are, well, it has to be a solution. So in the easiest case, it has to be a solution of the stationary Euler. And this is going to give us the new Reynolds stress. So the error from from this should give the new Reynolds stress. And for this one, for this identity, what we need is that, I put this in red because that's a key point, the average over one cell of this periodic vector field should equal to RQ. Okay. That's the basic argument in any scheme, any convex integration scheme. Okay, and so there are various ansatzes, Mikado flows, Beltrami flows, and so on. But okay, so in principle for MHD, one has to do something like this. But before I tell you what happens with MHD, let me just say, so there's a connection to weak stability. So CF weak stability of the system, because imagine, so here, I mean, highly oscillatory, and so it means there is a sort of frequency lambda, which is fixed. Of course, then it's sort of lambda q plus 1. But let us not fix it for the moment. So let us actually take a sequence in lambda and then consider this, this perturbation. Then, so this lambda is the kind of frequency. This is large. And so consider the case lambda goes to infinity. Now, if lambda goes to infinity, yeah, of course, I should have said also the average is 0 of this W. So out of this information, weakly, W will go to 0. It's fast oscillating with average 0. So weakly it goes to 0. And because of this other information, the average, I mean, so the weak limit of this product, which is the product appearing in the equations, the weak limit will be UQ tensor UQ plus RQ, because it will be the average. Okay, that's a standard, I don't know, lemma used in homogenization as well. Okay, so so what you see here is that, of course, I mean, the goal would be, the ideal goal would be to replace this whole term by something of the form UQ plus 1 tensor UQ plus 1. So no new error. I would like to do that. UQ plus 1 tensor UQ plus 1. And of course, I'm not able to do that, so there will be some new error, but let's forget about that. Now, you see that somehow this construction is the opposite of looking at weak convergence. We want to undo the weak convergence, which is a form of averaging. And now we are back into this, into what people in the physics literature call Reynolds averaging. This slide. Okay. Good. So, let me see, where am I? Okay. Okay, and so a typical result, I don't want to mention all the work on convex integration for Euler now, but just a typical result for B equal to 0. This was work with Camillo long time ago, or 2008. Is that, which is in the sort of L infinity framework, is that if you have a U bar, which is a solution of this system, so there is some Reynolds stress, this would be the sort of Reynolds averaged Euler, and R is strictly positive, with positive definite tensor, then there exists U, which is bounded, which is a weak solution of Euler, such that the energy of U is equal to the energy of U bar plus the defect, what is given by the defect. Okay, so so this way, I mean, compared to closure models and Reynolds averaging in physics, here we are not saying there's an equation for R bar. We are just saying that if you look at any R bar with this condition, positive definiteness, then I can construct, I mean, there are weak solutions, and of course there's actually a sequence of such weak solutions that would weakly converge back to U bar. Okay, so this is the way of undoing the weak convergence. Now, let's go back to MHD, because the situation is more interesting. In MHD, there is a diff curl structure. So now, of course, speaking in this seminar, I guess the French expression would be bringing back water to the river. In English, bringing coal to Newcastle. In German, we bring owls to Athens, which I don't know why this is the German one, but okay. In Czech and Polish, it's bringing wood to the forest. Oh, it's interesting, telling you something about the different cultures. So here, I mean, the diff curl structure is completely obvious. It's the Faraday system. It's already in diff curl form. I mean, you have, and of course, E in the ideal case is by Ohm's law is given by U cross B, or B cross U. So this would be the Faraday system. And then, of course, a typical, I mean, diff curl type result is that if I have a sequence, EJ converging to E weakly in L3/2, BJ converging weakly to B in L3, is then EJ dot BJ is converging, and this is a distribution, to E dot B. Okay, so I believe this is actually a theorem of Tartar in the 1970s. Okay, so of course this can be generalized to any Hölder dual exponents, but why am I saying this B L3 and E L3/2 is because if you remember the Kang-Lee result, there B was L3 and U was L3. So that case is exactly related to the same exponents. Okay, right, and so why is this E dot B an important quantity? It's a weakly continuous quantity, at least if we have this integrability. It's important because dH dt for the Faraday system now, not for the MHD, but Faraday system, is equal to -2 E dot B. Okay, so of course, if I'm in MHD, E dot B is 0. And that's the explanation of the conservation of helicity in terms of diff curl lemma. And now, okay, and so actually what we now, one of the things that we proved now with, but it's still work in progress, is that, well, maybe, sorry, there are two things. So, okay, so let me say, so, yeah, sorry, I'm jumping ahead of myself. So if you have a solution of F of the Faraday system, and let's say B is LP, E is LP prime, then helicity conserved. Okay, it's a very simple argument based on more or less the same type of proof as the diff curl lemma. And now what is work in progress is that okay, I need to clean the board. So let me call it actually a theorem. Is that so for all functions of time, which are reasonable, let's say, I don't want to be too precise here, and positive delta, there exist BE, which are weak solutions of this Faraday system, such that B is uniformly in time in the weak Marcinkiewicz space, LP infinity, so they just phase to be LP, E is uniformly in time in the corresponding P prime Marcinkiewicz space. And the magnetic helicity of this B is arbitrarily close to this prescribed function for all T. So it sort of tells you that the previous result is optimal. As soon as I go a little bit below in the integrability, I can do anything. Okay, and let me just say that, so this construction is based on a staircase laminate, if there's some experts in the room, in the audience. Okay, and coming back to MHD, that's my final message is, okay, so I won't call this relaxation, but relaxation in the mathematical sense, not the Voigt-Taylor sense. With this, well, diff-curl lemma or diff-curl structure, we can identify the correct averaged equations. So different from what people in physics do, we should look at the equations. Okay, so there's the B, and there is the hydrodynamic Reynolds stress, which now doesn't have a sign because there's the B term. So this is as what is in physics books. Then there is the B equation, which we can keep in this form. We have the divergence-free conditions. And with the additional condition that E dot B is 0 for almost every xt. Okay, so this should be what I want to call the averaged MHD system. Let's call it A MHD. Okay, so what is, I mean, in the physics literature, I was not able to find this condition, but this is very important. Because with this additional condition, what we can prove, and now I'm just going to state a very rough version, so FLS, rough, and work in progress. So if there is a post edit of the video, remove this. No, I'm just joking. It's okay. So for any solution of this system, solution of MHD, averaged MHD, there exists a weak solution, which is the weak solution of MHD with HB, I mean, equal to HB bar. And so I didn't really say that, but so basically this is that, so the Elsasser variables can be prescribed within some bounds. So this Z plus minus is essentially the total energy plus or minus the cross helicity. Okay, and so it doesn't fit here, but basically U and B will have the same integrability as, I mean, given by the integrability of U, B, E, and R. Okay, and there are many conditions, but I don't think it's appetizing to write down. So the message is that there is a strong connection between applications of convex integration to ideal fluid dynamics, motivated by certain phenomena of turbulence. And if you want to apply that to MHD, it's important to first identify the correct relaxation, which has to include this condition. And with this condition, we can recover. So in particular, if this U, B, E, R are bounded, then of course we have a conservation of magnetic helicity and at the same time, the Elsässer variables are something that can be prescribed. So we can have a fast relaxation of kinetic energy and slow relaxation of magnetic energy. But also this theorem can also be used to give counterexamples just below the Kang-Lee scale. So if I combine this result with the previous one, so first I construct here B bar and E bar, let's say, which are solutions of the Faraday system, and have magnetic helicity, which is somehow, I mean, let's say not constant. Then that can be combined with an additional convex integration step to derive. I mean, here U bar would be 0. You could set it to be 0, and then you can get a weak solution UB, which is just below L3 integrability. So in the Marcinkiewicz class, L3 infinity, such that the magnetic helicity is not conserved. So that's the end of my talk. Thank you very much for your attention.
Thank you very much for this very nice talk, which was indeed as close as possible to a Blackboard talk. Are there questions in the audience? You can raise your hand. Otherwise, I'll start with a couple of questions of my own. Okay, so maybe I'll start just to start the discussion. So I had two questions actually. In the lemma you showed at the end with the P prime, P indices. So here you don't have any restriction on P and P prime, right? They don't need to be 3 2/3.
Yes, this one.
Yes, yeah. So you have one first lemma in which one of them is 3 and the other one is 3/2. But then, yes, in this one.
Yeah, this also works in P prime and P.
Ah, okay.
Yeah, I just put that because that's.
Yeah. Okay.
Yeah.
Okay, so it's okay. Okay, so that.
I think so. I have to check. I'm not sure. Takar proved in this paper. I think it's 77. So it's.
I think he's in the room. So.
He's in the room. So you can say, but I'm pretty sure it's proved in the general case in the paper.
Okay. Professor Tata, if you want to answer the question, please feel free to do so. Otherwise, I had another question, which was so in the work you did on convex integration for Euler, the Beltrami flows played an important role, right, in the construction of the solution. I'm guessing that here the geometry of the solutions that you're constructing is even richer, perhaps. In MHD, is the analog okay? So do you also use these Beltrami flows, or is the equivalent this staircase laminate that you were mentioning?
Okay, so yes, so let me. So first the Beltrami flow. So so this is the slide on Euler. This W was Beltrami flows in some of the earlier papers, but there we were trying to prove, I mean, construct solutions that are not just bounded but also Höder continuous, and their Beltrami flows were a very good class to be able to do that. We are not there yet. Of course, so a natural question would be. Anyway, I stated this in a very rough way. I mean, this weak solution is just L infinity. Well, L infinity, if these are L infinity, otherwise it's even worse, but it's certainly not Höder continuous. So, so that would be a natural question if you assume this subsolution is bounded or let's say even continuous. Can we construct weak solutions which are Höder continuous? To go up to this, I don't have that slide here. I mean this Piasov scale or Höder scale. So so that's I think that's still out of reach. I don't know how to do that yet. I mean, we're thinking of that as well. So at the moment, the type of the type of perturbations that we use is much simpler. They are closer to plane waves. I mean, very simple perturbations of let's say some sort of linearized MHD system, where here we would replace this by some new name, S bar, and then everything is linear. But we still have this nonlinear constraint. So because of this nonlinear constraint, we are forced to choose what are called Clebsch variables. There is there's some tricks there, but it's not as, I cannot explain it so quickly, and it has nothing to do with Beltrami flows.
Okay, thank you. So there's a question of Maria Colombo. Please go ahead.
Hi, thanks, László. Maybe I had two questions. One is about, you have a result in Lorentz, right?
Can you
where
say,
you are.
Can you say again?
You have a result in a Lorentz space where you are barely outside.
Yes, this one. Okay.
Maybe can you comment how you get this fine?
Okay. So
Lorentz.
Yeah. So I mean, there is quite a long history of these staircase laminates, and the earliest type of results of this type are concerning determinant. But this is, of course, this B dot E. If this is divergence free and this is curl free, let's forget the time for the moment. Just think of functions, vector fields in space. It's like a determinant of some mapping, at least in 2D. It is. Okay. And for determinants, there's a lot of work of this type. That if you go below, so for instance in 2D, if you want to look at something like integral of the determinant being given by the boundary values. I mean, for instance, if U is even a diffeomorphism, it's just the volume of the set, so it's given by the boundary values, and this fails if du is not anymore L2. So this is a 2D case. So in particular, if it's L2 infinity, and these type of constructions. Yeah, I don't know how far I should go to the detail because it might take several minutes. But just to say that there's a long history of this type of things. Another example where this mechanism was used, or this idea was used, is in systems of the type, equations of the type divergence sigma x times grad u equals 0. Say again omega in R2. And sigma is just measurable, bounded between two values. Let's say 1 over lambda and lambda, and then of course a typical question is to understand higher integrability. So there's some p that depends on lambda, bigger than 2. And just to show that in general you cannot expect to go above that p lambda if you don't assume anything more about sigma. So it was used, so they are not in anything better than this plus epsilon. So staircase laminates have been used for this type of critical integrability. I don't know, Anne-Laure should decide if I can go on. I'm happy to go on, but...
I didn't see anyone else raising their hand. So if you have a question, please raise your hand. And otherwise, I think you can keep going on with the explanation. We still have a few minutes. Okay. So please, yeah, you can take a
okay, so just a couple more minutes. So the simplest example is I mean, you have laminates. So laminates are probability measures. Let's say nu on the space of matrices. So in these easy examples, determinant, I mean, Jacobian determinant in two-dimensional domains, this would be measures on the space of matrices that arise. So du would take values in space of 2 by 2 matrices, and so you take a probability measure on 2 by 2 matrices, but they are constructed along rank one combinations, these measures. Not any probability measure is a laminate, but the ones that are constructed by this sort of lamination along rank one lines can be constructed. So you can, so in principle, there are lemmas of the type that given a laminate nu, you can construct maps, say from this omega in R2 to R2, such that the push forward of Lebesgue measure of say normalized Lebesgue measure on omega is equal to this nu up to some small errors. Okay. So a simple case is when you have two matrices A and B and the difference is rank 1, then a typical laminate would be lambda delta A plus 1 minus lambda Dirac at B. So here rank of A minus B should be 1. And then you can find the mapping, which is of this type, where it's sort of like a roof type mapping. Okay, so that's a basic story. And then these staircase laminates would be where now you try to push mass to infinity. So for instance, if I have, let's say, diagonal matrices, X here and Y here, then rank 1 lines are the horizontal and vertical lines. And the staircase laminate is where I start somewhere. This would be the barycenter, and then I start splitting, and then keep splitting this measure along a different rank 1 line. And then this way go up to infinity. And so you will produce an infinite order unbounded laminate, such that its integrability will somehow be given by how much mass you keep pushing out. Okay, and the integrability, for instance, in this case, it's a good exercise, would be exactly L2 infinity. So it just fails to be L2 if you with this picture.
Okay, that's very enlightening. Thanks a lot. Are there any other questions? No? Well, if not, let's thank László again for a beautiful talk. And
thank you for the
congratulations on the setup. It was really I enjoyed it a lot. It was very readable and yes, it was nice.
Ah, good. I'm happy to work.
There is a François. François has a question. François, vas-y.
Yeah, I just would like to. This is a comment. I guess that the Diffker lemma in LP prime setting appears in my first paper about compensated compactness in 78.
Okay, I'm sorry.
No problem. Okay, and
does it appear with the T?
No, okay, it was no time. No time. Okay.
There was no time to write it, or there was no time?
No. It was written in the stationary case.
Okay.
Okay, and that I'm sure of that. And this was a paper. Okay, would. Okay.
I'm sorry. 78.
No problem. Actually, all of those papers was the result of joint work with Luc, okay, where Luc played the prominent role, of course. And okay, it is okay. I guess that there is an acknowledgement to him in the introduction, but a very few lines. Actually, this is a Tartar-Murat paper. Okay.
Okay. Yes. I was sorry. I was just referring to specifically this case with the T.
Yeah.
I mean, the only reference I found is a paper by Tartar from '77. I think there's one paper in '77 where this is explicitly mentioned with the T. That's why yes, but of course, thank you.
No, but no problem. Okay, I have no
because
problem.
I can change the slides.
No, but I have no problem with Luc, and Luc has no problem with me.
Oh, very good.
And I have no problem. This was at that time a joint work, and we published things which were in some sense some preliminary versions. Okay, and but no problem. I don't claim that this is specifically mine. This was okay. You know, the difficult lemma was proved in, okay, I guess something like 74, and was not published and not mentioned to anybody for 3 or 4 years. Okay.
Wow.
So, but no problem. The first time the name compensated compactness appeared on the paper is, I think, in my paper of 78.
Okay, good.
Okay, and no problem about that. Also, Luc mentioned that in, teach that in his cours PECO, which was in 77 or 76, I don't know. I don't remember exactly. But, okay.
Let me just maybe mention, since we are in this discussion, I like it very much. Thank you, Francois, for explaining the history. So concerning the time-dependent case, I was not able to find so much, but and at first sight, when I looked at this, I thought that the time is just some parameter. You're using the space, the standard diff curve. Yeah. I learned as Tartar-Murat lemma. You use that and then somehow try to deal with time as a parameter. But then I realized that okay, that would be helpful for references for this, because I'm sure it's well known that this space-time version is best written in terms of differential forms.
Yeah, but you know, I guess, and I'm quite sure that the case with the time goes into the general setting of the compensated compactness, which I agree, the general setting is written for L2 vectors. Okay?
Yes, so because this is xt, so this is space-time.
Yeah, okay. I agree. You know, yeah. What is okay? You can find in the first paper where compensated compactness appears in 78. You can find the case where that you mentioned. This is a case where you are LP prime in xt together. Okay, this is not the case where you are L infinity with value in LP prime and okay, or LQ with value in LP and LQ prime with value in LP prime, or things like that. But in this paper in 78, you have the case with the global variable t and x, a new variable zeta. Okay? It was done at that time. Okay, and the general case where you look. Okay, no. Okay, wait a second. I'm misleading. the convergence of the energy, e.g., bg, ej, bj goes to ab, is okay if you have those convergences in the station. Okay, in the stationary case. Okay, I guess it. Okay, I don't know. Okay. In any case, this is, for me, this is not really important. What is important, you know, is the fact that at some time people were, okay, the idea is that you can pass to the limit in a product without having a strong convergence and a weak convergence. This appeared as compensated compactness. Then you can make a lot of variation of the term, and in particular pass to various different spaces. At the beginning, the basic space was L2, okay? And then there are variants with LP, LP prime, and so on. And that's good that there are many variants. And I don't claim that I did that first, you did that first. This is not of interest for me. Okay.
So I think maybe, you know, I think I like this history, but what I find amazing, we are talking almost 50 years ago.
Yeah.
And when I look at recent books, recent papers by physicists on MHD turbulence, I see this. I see that they are just looking at, you know, they are taking bar and they understand that there is a difference between doing the bar like this or doing like this, but they're completely missing compensated compactness. And I think that's a very simple but very important additional information that has to, as I said, we are talking 50 years of theory in mathematics that has not infiltrated the physics community. So
yeah, that's a pity. That's a pity, but okay. We are fortunate that we were able to do that before of the physicist.
But it would be high time to let them know what.
Yeah, okay, no problem. Do it if you succeed. No, but I agree. But you know what is important, in my opinion, is uprising of this new idea. Then the details that once you did the first big result, which was the Diffie lemma. Okay, and to be more precise, this was the Diffie lemma in the L2 setting in 3 dimensions. Okay, and this was done. Okay, Luc did that. Okay, I guess in 74. Okay, and then this work, okay, was unknown of anybody except Jacques-Louis and Louis Nirenberg for 5 or 6 years. And Lyons asked me to write that in my thesis. And at the end, I wrote that in my thesis. And Luc told me, you know, okay, I said to Luc, we should have a common paper. He said, no, okay, I'm already in the career, you're not, you're young. Okay, he's just 1 year more than me. You're young, so you should publish paper, so publish it. And okay, next paper, we will do it together. Okay, and we have no problem. I have no problem with Luc. Luc has no problem with me. Okay, what is the most important for me is the fact that this new object appeared, and very quickly we realized that it was a general setting in L2. This is, okay, it's true that this is written in L2 when you have a sequence of vectors which converge in L2 to the power k, and those vectors have satisfied differential constraint such that, okay, such that the constraint that you write in the Faraday case, that some first order derivative with constant coefficients are in L2, or more exactly compact in each minus 1, in your case, equals to 0. Okay? Then you can characterize exactly the matrices M such that M U epsilon converge to M U U. And this is written in the paper of 78. Okay? This is written not in the optimal form. Actually, Luc found the way of writing the optimal form during the seminar I gave just before my thesis. Okay? C'est la vie. Hein?